Good morning, students. So today we will continue the same topic. We are talking about dynamic programming. So let's share my PPT first. So let's discuss elements of dynamic programming today. So before that, we must recall our previous two lectures where we have discussed uh, dynamic programming, the basic principle of dynamic programming, and two different problems, optimization problems basically. One is rod cutting problem and another is matrix chain multiplication problem. In both the problems, when you have gone through, you have understood that what kind of properties or characteristics an optimization problem must have so that we can use dynamic programming to solve them. So those are actually the elements you can say of dynamic programming. So dynamic programming is an approach, and using this approach we can solve many optimization problems which exhibits this kind of elements or the characteristic we'll be discussing today. So first we will try to understand then when should we look for dynamic programming solution to a problem. So as already we have discussed that there are two main characteristics of one optimization problem must have to apply dynamic programming. One of them is optimal substructure property. So in optimal substructure property, what we have understood that the basic idea is in an optimal solution to a problem or subproblem, it contains optimal solutions to the subproblems. That means what? We will find the optimal solutions for subproblems, subproblems actually, and then using those optimal solutions, we can create or construct an optimal solution to the original problem. So that is called optimal substructure property. Okay, so it must hold by an optimization problem to apply dynamic programming to solve it. Now, here we will try to understand that always for any optimization problem can we apply this? No, that we know. But sometimes what happens that mistakenly we assume that a problem can be solved using dynamic programming even it is not possible. Okay, so let's take an example. Suppose we have one directed graph, unweighted directed graph. So we want to find out optimal shortest path between any two vertices. Okay, optimal shortest path is one problem, and another problem is the unweighted longest simple path, longest. So first one is shortest and second one is longest shortest path. So if we see in the graph, in the given graph, so that will help us to understand this thing. But before you see, for the first problem, unweighted shortest path, suppose we have one vertex, initial vertex u and another vertex is v. Okay, and we want to find out a simple shortest path. What is a simple path? A path which does not contain any cycle or loop. Okay, because otherwise it will increase the length maybe. Okay, so that's why we will consider a simple path. So here we want to find out a path from u to v, so it will be a minimum one, shortest path. So does it hold that optimal substructure property or not? That we want to see. Suppose we have one vertex in between these two vertices R. So we can say that u to R, there is a path P1 dash. If it is a P1, suppose, so it can be P1 dash and another vertex V to V, it is a path from R to V, that is P1 double dash. So if P, this path is optimal, then P1 dash must be optimal and P1 double dash also must be optimal. Otherwise, we will not get this P is optimal. So, how it is optimal? If P1 dash is not optimal, then must be some other vertex R dash. There must be some other vertex R dash. So, it should be optimal. So, when P1 dash is not optimal, what we will do? We will replace this thing. Suppose P triple dash. If it is the optimal, then we will replace this P1 dash by P1 triple dash. This is called cut and paste concept. Okay, so we will cut out this P1 dash, we will paste in P1 triple dash. Okay, so obviously this P path will contain two optimal solutions, suboptimal solutions, or solutions to the sub problems of the shortest path from U to R and R to V. So P will contain actually two paths. P1 will contain two paths, P1 dash plus P2, P1 double dash. So from this one we can say that unweighted shortest path optimization problem that satisfies the optimal substructure property. Okay, but if we without thinking that actually or you can see in excitement, what we do, we try to solve this unweighted longest simple path using dynamic programming. We can guess that it is also can be solved using dynamic programming because it is similar to the unweighted shortest path problem. But you can see that if we have the similar kind of problem where we want to find out longest path from this to this, simple longest path, then it may not be always that P1 dash and P1 double dash both are longest simple path between U to R and R to V respectively. So we can check that with this example. Suppose we want to find out the shortest path from Q to T and there is an intermediate node R. So this shortest path from Q to T, it is like Q, R and T. And there is a shortest path from Q to R and R to T. So it is okay for weighted shortest path. But when we are talking about unweighted shortest path, then when we are talking about unweighted longest path, so the unweighted longest path, simple longest path from Q to T is this one, Q, R and T. But it doesn't mean that it is holding optimal substructure because there is an intermediate node R, and it is not that Q to R this is the longest one or R to T is the longest one, because if we see here Q to R, the longest path is Q, then S, then T, then R. This is the longest path. And R to T, the longest path is R to Q to S, then T. So the optimal path, actually longest optimal path, Q to R and T, it is not a combination of these two optimal solutions to the sub problems of finding the longest simple path from Q to R and R to T. But in this case, for simple unweighted shortest path, it is satisfying. So in excitement or whatever, without having the proper idea of optimal substructure property for all the problems, we cannot apply this thing always. So that we need to know that where we can apply this dynamic programming approach, we have to find out whether at all the optimal substructure property or optimal substructure condition is satisfying with the problem. Then we can apply. The next one is the we want to see that when we can apply this dynamic programming, always you see it is not that a problem which is showing optimal substructure property, it will also be solved using dynamic programming. So that is one condition that should be satisfied, or that should be fulfilled, so that we can apply dynamic programming. So that is one step decision, you can say. But we need to have one more step to be satisfied, or one more property to be satisfied when we apply dynamic programming. So first of all, that it should be overlapping subproblems property. That means one subproblem or two subproblems actually may contain the same subproblems in them. Okay, that means in simple words you can say that the same subproblem appears in different subproblems. Okay, so and the distinct number of subproblems being appeared during the solution procedure, that will be small. If the number of distinct subproblems, subproblems, or subproblem you can say is very high, then it is not useful. The direct programming is not at all useful for those problems. Okay, or it is not very intelligent idea to use that one. Okay, so the subproblems must be small, and the number of subproblems should be bounded by the polynomial in input side. Okay, and as I said, that overlapping subproblems is kind of thing that the same subproblem may appear in multiple subproblems. Then instead of solving the same subproblems again and again, we can solve once and then store in a table, and then finally we can use it by looking up the table when we need. Okay, so this figure is showing that idea that how the recursive procedure, if we use a recursive procedure to solve the matrix multiplication problem, okay, so the recursion will call the same call the function for same subproblems repeatedly. So here you can see that the algorithm we have already discussed, recursive matrician problem, where you see that for smaller subproblems, what we do, we try to find out an index between two matrices I and J, or you can say AI and AJ. Okay, in between them there are other matrices. So what do we want to do? We want to find out an index K between I and J, and we split the sequence into two subsequences, this and this. Okay, and we again apply the matrician recursive procedure for these two subsequences. Okay, so this is a recursive procedure, and here you can see that the same subproblems appear again and again. So this is the recursion tree for this procedure, and the size of the length of the matrix chain is 1 to 4, and you see recursively when you calculate this one, the same problem, suppose here you see 2 4. Okay, 2 4 appears in many places. Again 3 4 appears here. Okay, so you can see the shaded part of this tree are showing that they have already been solved in some step of this recursion, but again they are appearing in other subproblems. So if we use recursive procedure, this tree will be very big in structure, and the number of recursion or recursive call will be exponential in terms of number or in terms of time complexity. So that's why the idea of dynamic programming is to solve one subproblems when it appears first, and then store in a table, and when that subproblem appears again in any recursive step, that can be used or looked up into the table from the table and can be used. Okay, so this is a recursive, and that from that one we can calculate that how much time it takes the recursive procedure for matrix multiplication. So from the algorithm we can say some steps are constant, like these steps are constants, comparing and these things are constant. So you can say for if the matrix is chain is of length 1, then it must be a constant one. So we can represent using this notation, T1 equals to greater than equals to 1. But if there are n number of matrices, okay, then what we are doing, we are splitting that chain into two parts based on a certain index k, and then we are getting two subproblems of length k and length n minus k. Okay, so the total cost of calculating or finding the solution, matrician problem solution, that will be for any possible value of k from 1 to n minus 1, because we don't know which k value will give you the optimal solution. So that's why we need to explore all possible paths of the recursion tree, and we can find out. So this thing can be reduced in the form of this one, because from this one what we can see that Tk and Tn minus k both will be giving the same Ti for all the values I to n minus 1, because when k equals to 1, this will be T1 and this will be n minus 1. When k will be n minus 1, then it will be 1 and it will be n minus 1. So you see the same term will be repeated twice, or it will appear twice. So that's why we can reduce this thing expression in this way. Okay, so this form we are getting for the recursive matrix multiplication time complexity. And using any substitution method, we can find out that the time complexity or the Tn is omega of 2 to the power n, that is exponential. Okay, so that's why to avoid this kind of exponential operations, we need to use the kind of idea the dynamic programming approach provides us. So by looking into that, whether that optimization problem is having the certain properties like optimal substructure and overlapping subproblem. So these two things appears, then we can go for dynamic programming solution instead of this recursive matricial multiplication. Okay, but there is another way, like using recursive procedure. We can when a particular recursive function is called for any input size, then instead of going for calculating or recomputing or computing that function or finding the solution for it, what we need to do, if we consult with one particular table, okay, where we store the solution for a particular input size, and that is called memoization. That means we are memorizing the solved solution, and that by applying the table concept or using a table to store that result. So when again in any recursive procedure the same sub problems appears, then before going to calculating it or computing it, it consults with the table. Okay, if this is the first step of the lookup chain, you see that we calculate. So without calculating it checks whether the value is less than infinity. Okay, so that means it is not zero actually. It does mean that the value has been computed before. Okay, and then it is returning this the value. So instead of computing again, we are returning this value. If that value is not there, then using the simple calculating procedure, what we are doing here, that this thing we are using, and by comparing with the key q, which is a small value. So if it is smaller than greater than this one, we are storing this in this way. So this thing already we have discussed. The only objective of this part is that to make you understand a little bit in depth, like to understand where actually you can apply dynamic programming and what is the difference between dynamic programming bottom-up approach and top-down memoization problem. Memoization is also kind of technique where we use the recursive procedure, but instead of solving the same problem over and over, we just store the problem solution once in a table, and then we can use it further when the same problem appears again and again. So this memoization actually reduces this omega 2 to the power n time complexity algorithm into order of n cube time algorithm. So both the approaches, dynamic programming using bottom up bottom up approach and the memoization top down approach, both are showing the same time complexity, that is order of n cube. So this is actually, you can say, the recall of the two problems we have discussed. And before going to discuss one more problem which uses dynamic programming for the solution, we needed to discuss the elements of dynamic programming. Now we'll come to another problem that is also an optimization problem, and we can apply dynamic programming to solve it. So that is called longest common subsequence problem. So longest common subsequence problem, it has huge applications mainly in DNA matching or DNA sequencing and other computation linguistics and bioinformatics. Okay, where we have long sequences and we want to find the match or common pattern among them, we can use longest common subsequence uh, problem and find this optimal solution for the problem. So here you see we have a DNA sequence, this one. So we are not going in detail that what is a DNA. So DNA, we know this is a biological term, and it is a DNA strands consist of number of acids. Okay, so these are adenine, go, cytosine, go, thiamine, and one more G. So these the characters are showing the first character of the corresponding elements or the seeds. So you see the two sequences we have is S1 and S2. Okay, and what we want to do? We want to find out the similarities between them, because this is a huge application in bioinformatics where we want to find out any new existing DNA from any kind of you can say life, okay, or any kind of substance you can say, and we want to find out the similarity between them so that we can have an idea of uh, how much similarities with that existing one. Okay, so this is a application related thing of longest common subsequence, but we are interested to solve these problems. When you have two sequences, then we want to find out how similar they are. So before that, we have some terms to discuss. One is subsequence. So subsequence of a sequence is nothing but the same sequence by opting out zero or more elements from the sequence or characters from the sequence. Okay, so mathematically we can say that if it is x is a sequence and the characters symbols within it is x1 to x mi, or okay, so there may be a subsequence z of x, such that the if we can arrange this this order, increasing order I1, I2 to Ik, where xij equals to zj. That means there is an increasing sequence of or index of the elements of x, okay, and there must be a corresponding element in x so that it will match with the element in z. So you can say z is a subsequence of x. Okay, so all the elements of Z are present in X, okay, in increasing order sequence. Suppose this example we have Z equals to this one and this subsequence of X. How we can say? Because the sequence you see, the indices of the elements in X that we found here, that is 2, that means B is present in index 2, that is 2 here, and 3, that means 3, the C is 3, so it is C also, and B, that is 5, that means 5 is this one, 4, 5, so this is D and this is D, and then 7, this is B equals 7, so it is 7. So you can see the 2, 3, 5 and 7, these are the indices, increasing indices of the elements present in X, which are matching in increasing order of the elements of Z. So that you can say that Z is a subsequence of, so this term subsequence, not a sequence, subsequence of X. Now common subsequences, we have two subsequences, two sequences X and Y, and then there is a subsequence Z which is common for both the sequences X and Y. So you can say Z is a common subsequence of both X and Y. Now this example you see X is having A, B, C, B, D, A, and Y is B, D, C, A, B, A. Then you can say BCA is a common subsequence. BCA because B, C, A. Okay, so you can take any order, but that should be increasing. Okay, and here B, C, A. So you can see from this the increasing sequence of A and Y, sorry, Y, X and Y, both are having a common subsequence BCA. Okay, so BCA, you can see that the C may be here. Okay, another C may be here instead of D. So you could have taken this one B, C, A this way. So there is no restriction. Only the thing is that there should be an increasing indexing of the elements in X and Y, and there must be similar elements in the common subsequence Z. Okay. Now we are interested to find out the longest common subsequence. The longest means that will give you the better understanding that how similar this subsequence is with a given sequence. Okay, so this is the longest subsequence we are trying to find out. So example is that BCA, as we say, BCA is a common subsequence of X and Y in this example, but it is not a longest. It has length 3. But we have another subsequence BCBA. That means here, just let me erase this part. Okay, so here you can say this B, and C, this C, B, this B, and then A. Okay, here also is B, C, B, A. Okay, we are not taking this in. So here from this way, you can see that BCB is a common subsequence of X and Y both, and it has length 4. So there may be other subsequences, longest common subsequences of X and Y. Okay, but in this case, there is no longest common subsequence than length 4. So it has the longest common subsequence BCB for X and Y. Okay, so the problem is to find out a longest common subsequence between two sequences. So here the simple definition of the longest common subsequence problem, we are given two sequences x1 to xm and y1 to yn, and we are interested to find out the maximum length common subsequences of x and y. So from this thing, before that we need to know a prefix of a given sequence. Prefix of a given sequence means the ith prefix of any sequence is the first I elements of the sequence. That means we have x equals to x1, x2, xmi. There should be this one. So the ith, that means xi prefix or ith prefix of x is containing the elements, first I elements of the sequence. So that is called prefix. Okay. So based on this idea, we try to find out the longest common subsequence from the reverse one of the given two sequences. So if x equals to abcbda and x4 is what? x4 is the fourth element, like up to fourth element, a, b, c, d. So a, b, c, d is the I4 prefix of x. Okay, or x4 prefix of x. X0 is empty prefix because there is no element of x. So it is denoting the empty sequence. Now, before applying dynamic programming for solving this one, two things, as I said, we need to see that two characteristics are being satisfied or actually the problem is holding. One is the optimal substantial property. Okay, so that means optimal substantial property is that an optimal solution will contain optimal solution to a subproblem contains optimal solutions to subproblems. So here two problems we are having x and y, two sequences, and z is the longest common subsequence we are assuming. So if z is the longest common subsequence of x and y, then from this one what we can say that if xm equals to yn, that means the last element of x and last element of y are the last element of the common sequence, last element of the longest common subsequence. So that means if zk is the last element equals to xm, yn. So from this one, this problem is reduced to find out the longest common subsequence zk1 between xm minus 1 and yn minus 1. Why? Because already the last element of the longest common subsequence we have obtained, or we have got from these two elements, last elements of these two sequences. So the longest common subsequence is reducing, or you can say as an optimal solution. We are trying to find out for sub problem for the longest common subsequence of xm minus 1 and yn minus 1. Okay, if it is not, that means xm not equals to yn. Okay, so two things may happen. If it is not, then if zk is not equals to xm, that means the last element of xm and ym are not same, and zk is not the last element of xm, that means xm is not part of this longest common subsequence, okay, which is denoted by zk, the last element. If it is not, then what would be the last element of zk, last element of z or zk? That must be in the longest common subsequence between xm minus 1 and yn actually, or y, the total y. Got it? That means last element of xm not equals to yn, and xm is not part of this the longest common subsequence. Then obviously this z is a longest common subsequence of xm minus 1 and y. In other words, oppositely, what you can say, that if xm not equals to yn and zk is not yn actually, that means z is the longest common subsequence of x and y n minus 1. Okay, so in this way you can see that the problem is actually longest common subsequence of xm and yn, but based on these conditions, the longest common subsequence is the longest common subsequence of smaller length, okay, of the two sequences. So here from this one you can say the optimal substructure property is satisfied here, that the optimal solution z that is the longest common subsequence of xm and yn, that is containing the optimal solution z, which is the longest common subsequence of smaller subproblems z m minus 1 and y, or x y n minus 1. So this is holding optimal substructure property. Then the next thing what we see, that in longest common subsequence, that is the overlapping subproblem. So before overlapping subproblem, we need to see that the optimal substructure property can be representing or creating one recursive solution for the problem. So recursive solution, how can you see? The we want to find out an optimal solution for the longest common subsequence, and that is the length what we are interested to find out, that is the longest length of the sequence. So along with that, if we want to find out the longest common subsequence also, or you can say the elements in the longest common subsequence, then we need to keep more information, like what we did for rod cutting problem, to keep the position or the index of the different position where we are cutting the split or splitting the rod. And in matrixin multiplication also we are keeping one table for keeping the index or the position actually where we are splitting the matrix. Okay, so similarly here also, if we want to find the elements in the longest common subsequence, we need to use another table, but here we are using one cost table that is denoted by C. Okay, and it is denoting that for any two subsequences, or say sequences actually, that is of xi and yj. Okay, so xi yj, so here it does mean that if one of the length, like xi is 0 and or yi is 0, that means one of the subsequent sequence we are taking as input is 0, length 0, then there will be no cost or no longest common subsequence. If I and j both are greater than 0, and xi equals to yj. That means the last element of the two sequences we are considering right now, or two sub problems, they are equal or they are part of the longest common subsequence. That means we are getting the length whatever we have achieved for the smallest one step smaller problem or sub problem. So that is stored already in the table index ci minus 1 and j minus 1. Okay, and we are, if there is a similarity between the two elements, then the length of the longest common subsequence will increase by 1. Okay, if not, like if xi not equals to xj, then what you can say, that either that xi is part of the xi element is actually within the longest common subsequence, like z in the z, or yj is a longest part of the longest common subsequence denoted by z. So we want to find out the maximum length in the table index ci j minus 1 if the xi is matching with the longest common sequence, or that means ji is not matching with the longest common subsequence, or you can say ci minus 1 comma j. Okay, so both these two sub problems we have to explore, that which one is the longest one, then we will take this one. So this is giving a recursive definition of the optimal solution of an optimal solution for longest common subsequence. Okay, so from this one what we can say, that any problem here, we also want to see that whether it is having or sub problem overlapping or not. We have x and y. So in x and y we are having two sub problems, xn minus 1, yn minus 1. So the sub problem for longest common subsequence problem, this one, they contain the longest common subsequence problem for the smaller problems xn minus 1 and y minus 1. Okay, and for other options also it is true. So from this one what you can say, when we are taking this one, if we take that xn is a sequence and y is a sequence. Okay, so from this one what you can say, that the sequence, the subsequence or the subproblem appears xn minus 2 and yn minus 1. So for these things also you can see, for any value of this n or I j here, okay, they are containing optimal solutions to the subproblems, like this one and this one. These are the subproblems. So it holds that overlapping subproblem idea or property. So then we can apply dynamic programming for longest common subsequence, and CI is giving or holding that cost of the longest common subsequence. Okay, or the length you can say. And from this one you can say that same the value, cost value, can be defined for smaller values of I and j recursively. So we can apply recursive part about this one. So both the properties, optimal substitute property and overlapping subproblem, both are being held here. So actually we can apply dynamic programming. So how would we compute the solution for longest common subsequence? Here we see that we take two sequences in this algorithm. Okay, and what it is doing, it is the length of these two sequences, and we are having two tables B, which is holding the information of an optimal solution. That means we can reconstruct the optimal solution using the information we store in B. Okay, that means we want to find out the elements of the longest common subsequence, and that will be stored here. Okay, and C is the length we are talking about, the optimal length of the longest common subsequence. Initially, for each row, like for zero length, as I said, that if x any of this x, I or j, any of these two, if is 0, then the length of the longest common subsequence is 0. So initially what we do, for any value of I, when y is 0, it is 0. For any value of j, that means for y, if x is 0, then it is 0. Okay, and then what we are doing, we are checking out the recursive part, like if xi equals to yi, that means the last element we are talking about. Okay, you see, reverse order. Okay, if the last element, the xi element is matching with yj. Okay, so that means the corresponding value, because we construct the tables from bottom now, so that's why we need to take the smallest value of I and j. Okay, as we have seen in matrix and multiplication. So similarly, in dynamic programming, what we do, we go by the size of the problems. Initially, we solve the problems of smallest size, then we go one step up, then using those solutions to the sub problems, we go one step more. So using the solutions to the sub problems, optimal solution to the sub problem or sub problem, we solve an optimal solution or find an optimal solution for sub problems. So that's why initially we store 0 for this, and then for smaller values of I and j starting from 1. So what we do, if we find that two elements are same, xi and xj, then what we do, we take the length of the previous value or previous cell of the table, and we add 1, because one more match we have got, so it is denoting the increase of length 1 when you are getting one match. Okay, and this part is showing what? This part is showing that we need to move, like if we have x this way and y this way. Okay, the elements are like x1, x2, like this one, xm, and we have, sorry, y1, y2, yn. So if they are equal, then what we need to do, the longest common subsequence will become smaller by reducing it to. So it will be like this. What we'll consider the longest common subsequence between xm minus 1 and yn minus 1. So the problem size is reduced by 1. So that arrow is denoting that the problem size is reducing, okay, one step back. So if it is not, like what will it do? We need to check whether which length, the preferred length, which is the largest, either xi minus 1 j or ci minus 1 j or ci comma j minus 1. So which one is the largest? Based on that, if we see that this part, like I value, the I value is reducing, that the I value in the lower row, actually lower row value. Okay, I minus 1, that means the row number we are considering, it is one lesser value than I. So what does it mean? That we need to reduce the row. So if this is a table, so what we are doing, we are just reducing the row. That means it is showing that if it is the ith row, then we need to see this row, I minus 1 row, I minus 1 row. Okay, that means what we are doing actually, here we are not finding match between yi and yn. So what we are doing, and it is not, xm is not zk, as we have seen, zk. So we need to see the longest common subsequence between y, the entire y, and x1 to xm minus 1. So that's why we are reducing the row by 1. If it is not, like this part is greater, so what we are doing, we are reducing the column number. So column number, that means it is showing this way, that means here yn is not equals to zk, so we need to consider this thing this way. So these arrows are showing that which particular elements or indices of the two sequence x and y, they are getting matched. Okay, so here is an example. We have two sequences x and y. So the first length 0, we are having 0 for this C table, all zeros. Initially what we do, and then what we do, we put the match between them. Here you see the match we are getting. The first B, okay, we are putting x in this way, in this row wise, and column wise this one, y. Okay, so what we are getting, that B is matching here, it is 0, Okay, it is 0, it is not matching. So we are going to getting 1, B is matched with 1, this part. Okay, and then this C and this C is matching. So the value was 1, here it is value is increased by 2. Then B is matched with this B, so value is increased 3. And then this A is matched with this, the value is increased 4. And then there is no match, so finally it is 4 maximum. So the longest common subsequence we get here, that is BCBA, and the length is 4. Okay, and from this one what you can see, that if we want to construct the optimal solution for the longest common subsequence, so what we do, if we see that I or J, any of these is 0, then we return that there is no longest common subsequence, it will return directly 0. If Bij is this showing this arrow, entry is showing this arrow, so this call actually be like this, Bx, and the size like this one, size will be Mn, because initially we call this value, so it will call this one, this thing. And if we see that if arrow is this one vertical, then it will reduce this value, I value. So I value means it will go up, it will go up. So you see the shaded part, it is going up. Okay, then when you see this arrow, this slanting arrow, up slanting arrow, so it will reduce the value of I and J both. That means it will be M minus 1 and N minus 1. So it will come here, you see this diagonal part. Okay, and again it sees this one up arrow or vertical arrow up, so it will go up by reducing the row value. When it is again getting slanting arrow, it is going this part. Okay, and then when it is so that horizontal arrow, it does mean that it is reducing the column size J minus 1, so it is going this way. Okay, and similarly for other steps, so the optimal solution we construct in this way, that first, this will print the x value, that is a, okay, reverse order. Then it will be this one b, okay. Then here it will be c. When you are getting this left, this slanting arrow, it is printing x. You see, so printing x means the value here, x value. Then when you are getting this one, we are printing b. Okay, so the longest common subsequence we are getting, that is BCB for these two sequences using this dynamic programming approach. And here you see the possible number of distinct subproblems we are getting here, that is order of m minus m into n. M into n, because why? See that the number of common possible subsequence, if we want to match a length of m, this is m for x and this length for y. So for each prefix or each possible prefix of m will be matched with this one. So here will be m possible prefix, and for each prefix it will match with all the elements, all the prefix of this one x, then sorry y. So the total time complexity you will be getting, that is order of m into m. So this is the longest common subsequence problem, and we have seen that how can you solve this problem using dynamic programming. So at each particular problem, when we want to solve using dynamic programming, the first thing what we have understood after discussing many problems, like 3 problems mainly, along with the elements of dynamic programming, what we have understood, that we have to use the dynamic programming when the problem is showing two characteristics or two properties. One is the longest common one is the substructure property, okay, and another is overlapping subproperty. So these are the two characteristics you must observe or notice, then you can apply dynamic programming. So the main objective to reduce the time complexity from exponential to polynomial by avoiding the repeated computation of the same subset problems when it appears again and again in recursive method, so that we can do. So I think you have understood the difference between the recursive procedure and dynamic programming and memoization. So memoization is a recursive procedure, but it doesn't compute the same solution, same problem, or solve the same problem again and again. It stores the value in a table. So that is the idea, and they are similar in time complexity, but the memoization technique is top down and dynamic program is bottom up. So thank you for today. So if you have any question, you can ask me now. Any doubt if you have, please. Any question?